Okay, so this first chapter in chemistry is very important because it's talking about the periodic table. Now, periodic table is not something that you're learning for the first time now. You've already learned it. You have learned the generations of different periodic tables by the different scientists or chemists. Do you remember this? This is just a brief summary of what you have studied in the ninth standard. Like first, we learned about the early chemists who just uh, discovered some elements and they classified them as metals and non-metals. They did not know too much about them. Okay, and then you had one scientist named Dobreiner. He created something called what? Dobreiner's, yeah, but it was called law of triads. Triads means here three elements that were grouped together. Those three elements had similar properties, and one property was that the atomic mass of the middle element was the average of the first and last. Atomic mass. Remember atomic mass, not atomic number. Okay, they were all trying to arrange elements according to their atomic mass or atomic weight. Same, atomic mass or atomic weight. Then next came Newland. Newland's was called Newland's law of octaves. Okay, Newland's law of octaves. What he discovered was that every eighth element, the properties repeated. Just like how on a musical instrument you have every eighth element or eighth note is same, right? So like that, he classified them in groups of 8 and he called them as Newland's law of octaves. But again, it was not very successful. He could not continue that octave law for all the elements that they had found out till that time. Then came Mendeleev. He had the most successful periodic table. He had left a lot of gaps in between to add the elements that were not found out at that time. Okay, this was so many years before they had not found all the elements. So he had left gaps, but there were still so many problems with his periodic table. Then finally, Moseley, he arranged elements not according to atomic weights. See, all of them arranged according to atomic weights, but mostly he arranged according to atomic numbers. And with that came the modern periodic table, which we use right now. You see which year? This is the year that he was born or found out, I think, I'm not sure. But you can say that almost the periodic table that we have right now is 100 years old. Okay. And all the elements are arranged according to what? Atomic? No, atomic numbers. The previous periodic tables were all arranged according to atomic numbers. Sorry, atomic mass. But the modern ones are arranged according to atomic number. I was just for the previous batch, I was just writing down the first 20 elements. You all know the first 20 elements, right? In this chapter, you will also have to learn first group elements, second group elements, seventh group elements, and eighth group elements. Okay, in order you have to learn them. So hydrogen, helium, lithium, beryllium. So 1, 2, 3, 4. What are those numbers? Like hydrogen is 1, helium is 2, lithium is 3. What are those
atomic numbers?
Those are atomic numbers. And what is the atomic mass? There was a way to remember it. You don't have to memorize it, but it is good if you know it. Do you know what it is? For all those elements, first 20 elements? Where is it on that?
So we have to do something.
What, Ahmed?
You showed a method to find the atomic mass.
Yeah, the atomic mass is either double or double plus 1. Did we make a table?
Yes.
We had made the table before, like in 8th or 9th, where we compared the atomic numbers with their atomic masses. And the atomic mass is always either double or double plus 1. Right? See, these numbers that we have written here, these are the atomic numbers. Okay? And the atomic numbers just go out normally from 1 onwards till the last element. Which is the last element? How many elements are there in the periodic table? There are 118 elements. Okay, so these are the 118 elements. The last element is over here, which is OG. Okay, yeah. So we are learning the first 20 elements were still smaller classes, but now you will not only learn the first 20. 20 is stopping at calcium. Okay, here you're learning the first group elements, then second group elements, then directly seventh group elements, and the last group, that is 8 or 0 group elements. Okay, these elements in order you have to learn them. Okay, so what we'll do is we'll just repeat all the elements in the each group. Okay, in the first group, look at the elements in the first group: hydrogen, lithium, sodium,
Lithium, sodium.
potassium, rubidium, cesium, and francium. Okay, these are the group 1 elements. Then group 2 elements: beryllium, magnesium, calcium, strontium, barium, and radium. Okay, then going to group 7. Group 7: fluorine, chlorine, bromine, iodine, astatine. Till there. Okay, and then group 8: helium, neon, argon, krypton, xenon, and radon. Okay, so you have to memorize these elements in order. Okay, then other than this, you also need to memorize group period 2 and period 3. So period 2, which is period 2 here: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. That is period 2. And period 3 is sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. That's easy because you've already learned the first 20 elements, so they're in that particular order. Okay, so what all you have to learn is groups. Which all groups? 1, 2, 7, 8. 0 or 8. And periods, which all? First is nothing, only hydrogen, helium. So that you know it obviously. Yeah, but second and third. Fourth, you know only potassium, calcium. After that, then it goes into transition metals, or not transition also, but we don't learn those. Okay, so that much. Now, why do we need to know this? Is because we have to arrange these elements in a certain order. In this chapter, you're learning something called trends in the periodic table. Trends means like what happens to the atomic size as you go down the group, or what happens to the atomic size as you go to the right of the period. Okay, so like that atomic size is one of the trend. Like that, you have around 6 or 7 trends that you're learning in this chapter. Okay, all right. We'll okay. Well, let's see what's next. Pardon me.
What is trends?
Trend means some characters and properties that you can see across the periodic table. Okay, we will come to that, but before that, we will just see what all is there in this chapter. Okay, yeah. So salient features of the modern periodic table, it's telling you that classification, you're arranging the elements based on the atomic numbers. Uh, Let me ask you something. What is common for all the elements in group 1? Why did they place all these elements in group 1? What is common? They all have the same valency. What is the valency of all these elements? Okay, before going to
Plus
valency,
one.
yeah, the simple thing is their electronic configuration shows that the outermost orbit has 1 electron. All of these elements, they have 1 electron in their outermost orbit. So what do they do to become stable? They donate that 1 electron. And so,
Donate.
yeah, when they donate that 1 electron, its valency becomes what? +1, because it loses 1 negative charge. So it becomes +1. Okay, what is common for all the elements in group 2? Their valency is +2 because they donate 2 electrons in the outermost orbit. Next, group 3's valency is 3 plus. Group 4's valency is 4 plus or minus. Group 5
-3.
-3. Group 6
-2.
-2. And group 7 -1.
-4.
And group 8 is 0. Right. So that is the reason why elements are in groups, because their valency is matching. Okay. Now, what is common for elements in a period? That is from left to right. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. What's common for these elements? Why are they in that second period? Come on, answer me. Minora, you have something to say? What is common for these elements?
I
Anyone?
think because only 2 and 8 are there, and then the last shell they're donating, or
Anna, they have two orbits.
Yeah, they have 2 orbits. Okay. Like lithium has 2 orbits. First orbit has 2 electrons. Second orbit has 1 electron. So all of this they have. You can see that. Yeah, look at the electronic configuration. Boron is 2 3, carbon 2 4, then 2 5, 2 6, 2 7, and 2 8. So there are 2 orbits. Third period. What is common for all the elements in third period? They have 3 orbits, right? Sodium, 3 orbits. Look at the electronic configuration. 2, 8, 1, 3 orbits. Next, 2, 8, 2, 3 orbits. Okay. What is common for all elements in group 4? They have 4 orbits, and so on. 5 orbits, 6 orbits, finally 7 orbits. Okay. So the period number tells you the number of orbits. The group number tells you how many electrons are there in the outermost orbit. Group 6 means what? Oxygen, sulfur, selenium. What is common for these elements? Why 6? What is 6 for them? They have 6 electrons in their outermost orbit. Okay, so that is how these elements are placed in this orbit. And who was the one who created the periodic table? Moseley. Okay. Then, yeah, so this is talking about how many periods are there. How many periods are there in this periodic table? 7 periods. How many groups are there? 18 groups. And these 18 groups are, some of them are A group and some of them are B group. Did you notice A and B written anywhere? See this, 1A, 2A, next 3B. So then this is all B group till here, 1B, 2B. And the next is 3A again. So you have A on both the sides and B group elements in the center. These B group elements, they're also called as transition metals. And you learn about them when you go to the 11th and 12th standard. So we are just skipping this transition metals for now. We're only studying the A group elements. Okay. What's that? Someone said something, Nathan?
I was seeing Rutherfordium.
What is it? Rutherford. It's part of the periodic table. Part of the period. Okay. Then groups 1, 2, 13 to 17. That is all the A group elements. 1A, 2A. 13 means 13 is also called 3A. 14 is 4A. 15 is 5A. Then 6A and 7A. Till here, these elements are called normal elements. Then between the B group elements, that's 3 to 12, they are called transition elements or transition metals because they're all metals. Then group 18 or 8A or 0 group. These elements are called what? Noble or inert gases. They don't take part in any reaction because they have 8 electrons in their outermost orbit, or 2. For helium, there are 2 electrons in the outermost orbit. But the thing is that they are stable. They don't need to react. Okay. Then, yeah. What else is there? Okay, this group 1 elements, they have a certain name. Do you remember what they are called? Alkali metals. Yes. Group 2A, alkaline earth metals. Then 3, 4, 5, 6, they don't have any specific name. 7 has a name. What is 7th group?
Halogen.
Halogens. And 8th group, we said the name, that is noble gases or inert gases or even rare gases. Okay. All right. The first element has just 2 periods, 2 elements. So we can call it the first period as the shortest period because it only has 2 elements. Next, second period has how many elements? 8. So that's a short period. Next, third period also has 8 elements. That's also a short period. Now look at the next one. The fourth period, how many elements are there? 18. Okay. See, this is 2. Then here in the transition, there are 10. And then here again 6. So that's 2 plus 10 plus 6. So that's 18 elements. So it's a long period. Next, group period 5. That is also a long period with 18 elements. Then group 6, period 6. Is it 18? It's not exactly 18 because see over here, you see this? Ln, that is lanthanides. See, lanthanides are from 57 till 71. These are the lanthanides. It's outside the periodic table. These lanthanides, you know how many elements are here? There are 14 elements. 14 lanthanides. So lanthanum is the first one, and totally there are 14 elements over here. Okay. So if you see the number of elements in that sixth group, it is 32 elements. How 32? This 2 plus 8, sorry, 2 plus 6, that's 8. 8 plus 10, 14. 14 plus 14. 14 plus 14? No. 2 plus 8, sorry, 8 plus 10, 18. 18 plus 14. 18 plus 14 is 32. Okay. So 32 elements in this period 6. And same way, period 7 also has a big group here in between that is called the actinides. That is starting from this element actinium till the end, Laurentium. Okay. So these are again 14 of them. I hope you remember. Let me just remind you. This first two groups, they were called the S block. You remember? SPDF. Anyone remembers SPDF? So this first groups, yeah, they're called the S block. Then these 6, that is called the P block. And then here in between this transition, they are the D block. And then here this part here, this is the F block. Okay, so you have S, P, D, F. Okay, you just remember how many elements are in each of these, how many groups. S block has how many groups? 2 groups. P block has 6 groups. D block has 10 groups. Correct? And F block has 14 groups. Okay, so you're adding 4 every time. 2, then 2 plus 4, 6 plus 4, 10. 10 plus 4, 14. Okay, so you can easily remember these numbers. So you're learning about which 2 blocks? Out of these 4 blocks, which blocks do we have till 10th standard? S and P. They are the simple elements, the normal elements. They have normal electronic configurations. The D has a very complicated electronic configuration, and F also the same. Okay. Okay. So period 1 is the shortest period. What is that, Ahmed?
I didn't get that addition. 2 plus 4 6.
S block has 2 groups. Okay. Then you add 4, 6. The P block has 6. Then you add 4 again. That is the number of groups in D block, 10. Then you add 4 again. That is the number of groups in F block, 14 elements. See, 1, 2, 3, 4. Like that, there are totally 14 elements, 14 groups.
Yes, sir.
Clear?
Yes, sir.
Okay. Yes. So period 1 was a short one, shortest in fact. Period 2 was short. Next also short. 4 is short, long. 5 is also long. 6 is longest. 7 is also the longest. Okay. Now, normally the properties are similar as you go down the group. Like lithium, sodium, potassium, rubidium, they will all have similar properties, right? But in some cases, the similar properties are diagonally. For example, lithium and magnesium have some similar properties. What is right below lithium is sodium, but you see some similar properties between lithium and magnesium. Similarly, between beryllium and aluminum, boron and silicon. So like this, there are some diagonal similar properties. When you see that type of properties, we call those elements as bridge elements. So you see some bridge elements in between period 2 and period 3. Okay, yeah, not a very important thing, but this is something. Bridge elements they are called when the properties are similar diagonally. Okay. Now, do we have metals or non-metals or what now? Let's just talk about that. What is lithium? Metal or non-metal? Here it's given in colors so you can see it clearly. Lithium is metal. Beryllium, metal. Alkaline earth metal. Boron, look at the colors.
Met-
Boron is metalloid. What's a metalloid? It has some properties of metal, some properties of non-metal. So it's not a metal, it's not a non-metal. It's in between. So that is a metalloid. Next, carbon, non-metal.
Non-metal.
Non-metal. Oxygen, non-metal. Fluorine, non-metal. And finally, neon,
Non-metal.
simple gas. So if you look at metals to non-metals, what happens? You can see there's a gradual change from metals to non-metals. On the left side, you see the metal, which is the most reactive metal. Then the reactivity decreases and it changes into non-metals. Then you see the non-metallic character is increasing. Like if you see carbon, nitrogen, oxygen, fluorine, fluorine is the most non-metallic non-metallic element or non-metal. Okay, so on the left side you see elements having the most metallic characters, and on the right side you see elements having the most non-metallic character. So you see a trend over here, changing from metals into non-metals. Okay, so in this they have shown everything about each of these periods: period 1, period 2, period 3. Okay, what have they shown? They've shown their group number, the element, their atomic number, their electron configuration, their state, whether they're metals or non-metals, and their valencies. Okay, now metals are, their valency is positive, right? So we call them electropositive elements. Electropositive. And when you go to the right, the non-metals have valency of minus. So they're called electronegative. You will see in the book some places it's written like this. Towards the left, you have electropositive character elements. Do you see that?
Sir, your voice is breaking.
Okay, so check your network. Okay, to the left, you have electropositive elements. Or you can say that the electropositive character increases when you go to the left. And when you go to the right, what happens? The electronegative character increases. This chapter is all about characters and properties. The trends are the characters and properties when you go to the left, when you go to the right, what's happening. Okay, we'll be seeing each one in detail, but here is just a summary of what you're going to see. Then the next you're seeing what happens when each of these elements join with other elements. How do they join? So let's look at how these elements join with oxygen. Okay, you have sodium joining with oxygen. Okay, we're looking at all the group period 3 elements. What are the period 3 elements? Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. So we're going to see how each of these elements react with oxygen. So does sodium react with oxygen? Yes. And what does it form? Sodium oxide. Okay. Now how the formula, what is the formula? So let us see each one. Sodium's valency is what? +1. And oxygen's valency is 2 minus, right? So when they join using crisscross method, what's the formula? Na2O. Right. This is the formula for sodium oxide. All right. Then next, after sodium, we have magnesium. How does magnesium join with oxygen? So magnesium's valency is also 2 plus. Oxygen is 2 minus. So what's the formula when magnesium and oxygen join?
Mg.
MgO. The 2 and 2 get cut. Next, you
Yes.
have aluminum. Aluminum's valency is +3. So when that joins with oxygen, what do you get?
Al2O3.
Al2O3. This is aluminum oxide. Next, after aluminum, what do we have? Silicon. Okay, how does silicon join with oxygen? Silicon's valency is what? Silicon's valency? 4. Because it's in the fourth group, no? All elements in the fourth group have a valency 4. It's either 4 plus or 4 minus. Depends on whether it's a metal or a non-metal. If it's a metal, we say 4 plus. If it's a non-metal, we'll say 4 minus. Silicon is not both. It's a metalloid. So you can say either 4 plus or 4 minus. Okay. Let's take 4 plus. Oxygen is 2 minus. So what is the formula for silicon oxide? You can cut 2 and 4. So if you cut 2 and 4, this will become 2, it will become 1. So SiO2. This is
O2.
okay. All right. Next, what's after silicon?
Can you hear me?
Yes. Okay. After silicon, what do we have is phosphorus. Phosphorus is P. Valency of phosphorus 3 minus. So it becomes a non-metal now. So can non-metal and non-metal join? See, all this was metal joining with non-metal. Can non-metal join with a non-metal? Yes, but it forms a different type of compound. Okay. In your second chapter, you'll be learning that in detail, but you've already learned that same chapter in 9th standard. Do you remember covalent ionic compounds and covalent compounds? All these metal with non-metals, what do we call these compounds? Ionic or electrovalent compounds. Electrovalent or ionic compounds. All what we have written here are electrovalent or ionic. What is an electrovalent compound is? When a metal joins with a non-metal, you notice that there is transfer of electrons that take place. The metal will donate electrons and the non-metal will take these electrons, right? That is what we see for all electrovalent compounds. Silicon, I don't know if we can consider that as electrovalent because I think sharing takes place here, okay? But for all metals, that is sodium, magnesium, and aluminum, we see the metal donating electrons and the non-metal taking electrons, okay? So this type of bond is called the electrovalent bond, and it's a very strong bond. Electrovalent bonds are very strong because one element becomes positive and one element becomes negative. And now when you bring positive and negative close to each other, what happens? They attract, right? It's like a magnet. You bring North Pole and South Pole close to each other, they attract and they form a very strong bond. So that is what we see for all electrovalent compounds. Okay. This chapter you're revising, 9th standard chapter you're revising again in the second chapter in chemistry. Okay, we'll be learning this again in second chapter. Coming to the non-metal joining with non-metal, what do we call these compounds?
Covalent compound.
Covalent compounds. Okay, covalent compounds. In covalent compounds, you see a non-metal joining with another non-metal. And because both are negatively charged, they don't have a very strong attraction between them. Okay, negative and negative don't attract, right? They actually repel. But one has more negativity than the other. So there is a slight attraction. And so these covalent bonds are not very strong. They're very weak. Okay. So what is the compound formed between phosphorus and oxygen? You can use a crisscross method again. So that is P2O3. Okay, there is P2O3 and there's even P2O5 because sometimes you see phosphorus having a valency of 5 plus. Okay, it just happens sometimes that it's 5 plus or minus. It should be plus, and chlorine has 2 minus. Sorry, not chlorine. Oxygen has 2 minus, and so you also see another type of phosphorus oxide which is P2O5. This is P2O3 is phosphorus trioxide and P2O5 is phosphorus pentaoxide. Penta means what?
Anna, your audio is getting cut off at the end of a sentence.
Okay.
Yes, sir. Now also.
Is it getting cut off for everyone? No.
No.
Okay. All right. So let me say that again. Naming also we have learned before, but just a summary. How do you name these elements? What is Na2O? Sodium oxide. MgO, magnesium oxide. Al2O3, aluminium oxide. No trioxide, dioxide, nothing. For any metal joining with non-metal, we just say the metal's name and the non-metal's name. No putting di and tri and tetra or penta or anything. Okay, when do we do that? Is when two non-metals join. When two non-metals join, for the second non-metal, you will mention the number of a number of atoms. Like P2O3, it's not just phosphorus oxide. What will P2O3 be? Phosphorus 3 is tri. So P2O3 will be trioxide. And P2O5 will be pentoxide. So phosphorus pentoxide. Okay. All right. Next, after phosphorus, we have sulfur. Sulfur's valency is 6. I mean, 6 electrons in the outermost orbit. So its valency is 2 minus. And oxygen is, both are 2 minus. Both. Okay. So it's supposed to form SO according to this, but it forms SO2 and SO3. Sulfur dioxide, sulfur trioxide. Okay. Yeah, so we don't get into that complexities of why these elements are formed, but the compound formed when sulfur and oxygen join are SO2 and SO3. Forms SO2 and SO3. And last, chlorine. Chlorine valency is 1 minus, oxygen is 2 minus, but again, it's a little complex of how these elements join, but you get something called Cl2O7. So in short, all of the elements are able to join with oxygen and form some compound. Okay. The first few elements, that is when the metals join with oxygen, we get electrovalent compounds. And when the non-metals join with oxygen, we get covalent compounds. The metals, when they join with oxygen, they form acids or bases. Bases, they're basic. And when the non-metals join with oxygen, we get acids. Okay. Then you also have, instead of oxides, you have hydroxides and hydrides. Same rule. Basically, just showing you how these elements react with different other elements. How they react with oxygen, how they react with hydroxides, that is OH, how they react with hydrides. What is an amphoteric substance? Do you remember anyone? Did we have this before? You will have this in the 4th chapter. What is an amphoteric substance? Okay, but in short, an amphoteric substance is something that can react with an acid or a base to form salt and water. What's an amphoteric substance? It's a substance that can react either with an acid or with a base to form salt and water. You know what's neutralization reaction, everyone? Neutralization reaction. Acid plus base gives salt and water. You've heard of that reaction? Neutralization reaction. So anyway, this is all coming in the later chapters. Okay, this is not what you're mainly studying in this chapter. In this chapter, we're going to look at trends. Okay, so we'll just look at a few trends, at least 2 or 3 trends we will do today. Okay, right. So here are some 5 trends are here. Okay, the first one is atomic radius. Okay, we'll look at the atomic radius. What is the definition for atomic radius? Ahmed, are you there? Nathan, Ryan?
Yes, sir.
Yes, sir.
Okay, look at the atomic radius. The picture is given here. It's like the radius of a circle. Right? How do you measure the radius of a circle? Circle. Radius. What is radius? It's the distance between the center till the circumference. Correct? This is radius. So same way for atomic radius. How do you measure the atomic radius? Is a distance from the center of the atom or center of the nucleus till the outermost orbit. Okay, so that is the atomic radius. Basically, it is the atomic size, the size of the atom. Okay, now which atom will have the smallest radius? Hydrogen and helium. Why? They only have one orbit, right? So as the number of orbits increase, what happens? The radius increases. Simple as that, right? So now look at the periodic table and tell me, when you go down the group, what happens to the atomic radius?
Decreases.
It increases, right? Because as you go down the group, the number of orbits increase. As you go down the group, the number of orbits increase, and because of that, the atomic radius increases, right? Hydrogen has only one orbit. Lithium has two orbits, then three orbits, four orbits, five orbits, six orbits, and seven orbits. So as we go down the group, the atomic radius increases. Okay, let's write the first trend, that is atomic radius. As you go down, what happens to the atomic radius? Increases. Okay. Now, as you go right along a period, for example, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, what happens to the radius?
Decreases.
Decreases, remains the same. Okay. Okay. We would generally say it stays the same. Why? Because the number of orbits are remaining the same. Along this period, all of them have two orbits. So the size is supposed to remain the same, but it actually decreases. Now, Minora, do you know why it decreases? Okay.
Anna, because the nuclear charge increases.
Yes, correct. That's the answer. Okay, but let me explain that one to you. Okay, now as you go to the right, the orbits remain the same. But what is increasing as you go to the right is the number of protons in the nucleus and the number of electrons in the outermost orbit. Right? Protons inside the nucleus is increasing. For example, lithium has how many protons? Lithium has how many protons? Three protons, three electrons. Beryllium has four protons and four electrons. Remember, protons is positive inside the nucleus and electrons is negative outside the nucleus. So as you go to the right, the number of protons and electrons are increasing. Okay, let's talk about the protons. Protons are increasing. That means the number of positive charges in the nucleus is increasing. And if there are more positive charges, it creates more charge, more attractive forces, and it pulls the outermost electrons closer to the center. When more positive charges and more negative charges, there is more attractive forces between them. And so what's happening is it is pulling the outermost orbit closer to the center. So as you go to the right, what's happening to the atomic size, everyone? It's decreasing because the protons is increasing. Instead of saying protons increase, we use another word. We say the nuclear charge increases. Basically, nuclear charge means the number of protons in the nucleus. Clear? All right. So once again, revision. As you go down the group, what happens to the atomic size? Increases because the number of orbits increase. As you go to the right, what happens to the atomic size? Decreases. Why? Because nuclear charge increases. You just have to say that much. The explanation is because protons increase, electrons increase, and so there is a more attractive forces between them. But it's simple. You just have to say, as you go to the right, size decreases. Why? Because nuclear charge increases. Okay. All right. So this way, decreases. It's very easy to remember. If anything increases when you go down, it will decrease when you go to the right. It's always opposite. Okay. If you go down and it decreases, that means to the right it will increase. Okay. As we see the different trends, this pattern you will see in all the trends. Down and right will be opposite of each other. That's very easy to remember. If you remember one of them, you'll know the other one. Okay. Okay, everyone just write down this. Write on the first, write the heading as trends in the periodic table. And write the first trend as atomic radius. We'll write the reason also in a bracket. All right, everyone clear on this atomic radius? First one? Okay, the second trend is called ionization potential. Okay, so we need to know this definition. What is ionization potential? So let's read the definition. It is the amount of energy required to remove an electron from the outermost shell of an isolated gaseous atom. Okay, so let's look at sodium, for example. Okay, now sodium has how many electrons in the outermost orbit? Sodium has one electron in the outermost orbit. Okay, now that one electron Why is it staying over there? It's because of the attractive forces from the nucleus or the nuclear charge. The nuclear charge is what is attracting and keeping that electron in its place. So now if you want to remove that electron, you need some energy. Because the energy to pull out that electron, right? That energy required to remove that electron is called ionization potential. You understand what is ionization potential? It is the amount of energy required to remove that outermost electron. So let's read the definition for ionization potential. It is the what? Amount of energy required, needed. Required means needed. Needed for what? Remove an electron from the outermost shell of an isolated gaseous atom. So they're talking only about gaseous atoms, not sodium or magnesium. Okay, but for example, we can use them. So now, if you um, look at chlorine. Look at chlorine. Now, chlorine has how many electrons in the outermost orbit? Chlorine has how many electrons in the outermost orbit? Chlorine has 7. Okay, so to remove those 7 electrons, you need more energy or less energy than compared to sodium. Sodium, you need energy to remove that 1 electron. Chlorine also you need energy, but would you need more energy or less energy than sodium? You need more energy. Why? Because chlorine has more nuclear charge. There is more attractive forces from the nucleus, and those 7 electrons are held more strongly. Okay, so you need more energy if you want to remove those electrons. That's why it's impossible to remove those electrons. Do you remove electrons from chlorine? What does chlorine do? It takes electron, it doesn't remove because the amount of energy required to remove is too high. Okay, is that clear? So this tells you what happens when you go to the right. What happens when you go to the right to ionization potential? Compares. It increases. Sodium has only 1 electron. Chlorine has 1, 2, 3, 4, 5, 6, 7, and 7. So chlorine, you need more energy to remove the electrons. Okay. So as you go to the right, what happens to the ionization potential? It increases. Is that clear? Now let's look at what happens when we go down. So what's below sodium on the periodic table? First group. What's below sodium?
Potassium.
Potassium. Okay. Now potassium also has 1 electron in the outermost orbit. Okay. But the thing is that 1 electron is more far away from the center because the size is big, no? See, sodium has how many orbits? Sodium has how many orbits? 3 orbits. Okay, 1, 2, 3 orbits. So this 1 electron is in the third orbit. The outermost electron is in the third orbit. Potassium has how many electron? How many orbits? Come on, everyone. 4, right? And so this 1 electron in the fourth orbit is more far away from the center, right? So that nuclear charge will be lesser for potassium. Why? Because of the distance, right? The farther you go from the center, there is lesser nuclear charge. And so this outermost electron is not held very strongly compared to sodium's outermost electron. So do you need more energy to remove that electron or less energy to remove this electron? Less energy because it's not held very strongly. Okay, so as the atomic size increases when you go down, lesser energy is needed to remove that electron from the outermost orbit. Is everyone clear with that? Okay, so in the trend, second trend, what do you observe? As there is ionization potential. When you go down the group, what happens to ionization potential? It decreases. The amount of energy required to remove the electron is lesser as you go down. Why? What's the reason? Because atomic size increases. Atomic size increases, and because atomic size increases, the nuclear charge decreases. You see, they're all related to each other. As the atomic size increases, the nuclear charge decreases, and therefore less ionization potential is required as you go down. And as you go to the right, what happens? ionization potential increases. Why? Because nuclear charge increases. When there's more nuclear charge, you need more energy to remove that electron from the outermost orbit. Is everyone clear with this? Okay. So write down the trend for ionization potential.
Now, do the electrons, protons, or neutrons have any change with the state of matter? The change of state of matter.
No, that number doesn't change. Whatever state the matter is, the number of electrons, protons, neutrons don't change.
Okay.
Change of matter has nothing to do with the atomic structure. It has to do with uh, the, the the attractive forces between the molecules, not even attractive
So
forces
can I
between atoms. Ahmed, we're almost done. 2 minutes and then you can leave. Okay. So this chapter is one of a small
Yes, sir.
chapter, but it's important. In this chapter, you're learning two things only mainly. One is these trends. How many trends are here? These five
Five.
trends. Okay, five trends. The fifth trend is non-metallic character and as well as metallic character. So we can say six trends. And the nuclear charge is not written here, but nuclear charge is used for each of these five trends. We use this word nuclear charge, right? So you're learning about these five trends. That's the first thing. Second thing is arranging these elements in arranging increasing or decreasing order of any of these five trends. For example, I'll give you some five elements and I'll tell you arrange these elements according to their increasing order of atomic size. Okay, so you should know, okay, where these elements belong to. Are they in the first group? Are they in the second period? Are they in the third period? You should know it, and then you'll be able to arrange them according to their increasing or decreasing order of whatever is asked in the question. So that is why it is important to know these things. What all you have to learn for the next classes? First group, second group, seventh group, eighth group. And periods, which are periods? Second period and third period. You should know these elements. Like when you see some elements, you should know where they belong. For example, let me give you one thing. Suppose I say boron, uh, lithium, beryllium, carbon, oxygen. Where do these elements belong?
Period 2.
Period 2. Right. So you need to know that, okay, these elements are in period 2. And then if I ask to arrange them according to their decreasing order of atomic size. Decreasing order of atomic size means from left to right or right to left. Decreases to the right. So when I say write in decreasing order means you should write them from left to right. If I say write in increasing order, you need to write from right to left. Okay. So like that. That will be seeing it tomorrow. Okay. So 2 days is enough for this chapter to finish. By tomorrow we'll be done with this chapter. Okay. But by tomorrow you need to study what all? Whatever I said. And these two trends, that is atomic radius and ionization potential. Okay. All right. We'll stop with this. I'll see you all tomorrow with chemistry. Okay, yeah, let's look at the same points that we saw yesterday, that is atomic radius and ionization potential in more detail, okay? Yeah. So what is atomic size, as I said yesterday? Atomic size is the distance between the center of the nucleus of an atom and its outermost shell. In other words, the atomic radius. Atomic radius and atomic size is the same thing. The unit for measuring atomic size is angstrom. How much is one angstrom? Angstrom, actually. Angstrom. I remember it as angstrom. How much is one angstrom or one angstrom? 10 raised to minus 10 meters. So that's a very
minus
unit. Okay, that is the unit to measure atomic radius. Then you have the distance between two different atoms, the center of two atoms. That distance is called bond length, or as in your book, it is called internuclear distance. Okay. So all of these trends, they depend on two things. They depend on the atomic size, like all the other trends depend on the atomic size and the nuclear charge. See, like as we saw here, or if you look at the next one, like when we saw ionization potential, we saw that as you go down down the group, ionization potential decreases as we go down the group because the atomic size increases. See, the other trends, they all depend on two factors. What are the two factors? First is the atomic size, and second is nuclear charge. Everything depends on these two, atomic size and nuclear charge. Okay, so they're two important um, trends that are used in all the other trends. Okay. Okay, let's look at the first one again. Atomic
Shells,
size.
no? It depends on number of shells.
What is it, Amit?
It depends on number of shells.
Yeah, number of shells. Orbit depends on size depends on the number of shells. Here's a list of all the elements of which group or which period. Lithium, beryllium, boron. These are all elements in which two? What two? Group two, not group two. Period two. Right.
Period 2.
Yeah, and as we go to the right of the period, what happens to the size?
Increase.
Yeah, nuclear charge increases, but what about atomic size? It decreases. Now, see here, they have given the radius. Do you notice it is decreasing? As we go to the right, you can see the numbers decreasing. Yes, and when it comes to neon, it again increases. Okay, so that is because like the reason is given over here. But as you can see, generally the size is decreasing. As you go to the right, number of shell, does it change? As you go to the right, number of shells are remaining same. All of them have two shells, right? Nuclear charge, it increases because the number of protons and electrons are increasing. Yeah, and here they've given a relationship. Since the nuclear number of shells remains same, atomic size is supposed to be unaffected. But because of that increase in nuclear charge, the atomic size is decreasing. Okay. Now, hence lithium has the largest atomic radius, 1.55. But neon has a larger atomic radius since it is inert. Since in inert gases, the outer shell is completely filled, resulting in a force of repulsion which increases the atomic radius. Why does neon have high atomic radius? It's because the outermost orbit is complete. Neon has 8 electrons in the outermost orbit, and these 8 electrons, they repel from each other. Okay, because they're all negatively charged, they all repel and it pushes the outermost orbit a little bigger like this. So that is why neon has a bigger radius, even though it's supposed to have the smallest radius, because according to the trend, it's supposed to have small, but it's an exception because it is the complete orbit and that electrons repel each other, pushing their outermost orbit a little outer, making it bigger. Down a group is easy. As you go down the group, atomic size increases. Why? Because orbits increase. As you go down, one orbit is added. And so there's a clear increase in the atomic radius. We see here lithium, sodium, potassium, rubidium, cesium. What elements are these? Where they belong? Group? Which group? Group 1. Right. So here you can see the size. Lithium is 1.55, then 1.91, 2.35, 2.48, and 2.67. So the atomic size is increasing as you go down the group. Reason here, number of shells increase as you go down, and because of the atomic size increases. Nuclear charge actually increases when you go down because number of protons are increasing, number of electrons are increasing. So according to that, the atomic size should decrease. That's what we saw before, right? If the nuclear charge increases, the atomic size should decrease. But why is that not making an effect over here? Because the shells make such a big difference in the size. So even the nuclear charge increases, that does not make any effect in the size. It's supposed to decrease, maybe it decreases a little bit, but as a new orbit is added, that orbit is makes it much more bigger. Okay. So the overall atomic radius increases as you go down the group. Clear, everyone? Any doubt in atomic size?
No.
Okay, the second trend, that is ionization potential. Okay, does anyone remember this? You all should know this, not remember. What is it? Tell me.
Amount of energy required to remove an atom.
Remove an electron. Hmm? So to remove an electron, you need some energy because these electrons are held together. The nucleus is pulling the electrons together. So if you need to remove an electron, then you need some energy, right? That energy required to remove that electron is called ionization potential. And we saw that as you go to the right, that energy increases because there's so much nuclear charge that's holding those electrons together. And so you need more energy. As the nuclear charge increases, you need more energy to remove that electron. Right. So as you go to the right, since nuclear charge increases, ionization potential also increases. Then as you go down the group, uh, atomic size increases. So there is lesser nuclear charge between the center and the outermost electron. And so there's not so much forces holding that electron, and you can easily remove that electron. So you don't need so much energy, just a less ionization potential is enough as you go down the group. In your book, ionization potential comes as the fourth trend. Page number 11. So ionization potential is also called as what? Ionization energy, or it's also called as ionization enthalpy. You saw those three different words? So when this electron is removed from an atom, what happens to that atom? What does it turn into? It becomes positively charged, right? So like here you can see this is the atom. So when the atom loses one electron, it turns into one positively charged ion. If the atom loses two electrons, then its charge becomes 2 plus, right? It loses two electrons and so it becomes 2 plus. So here they're saying, suppose an atom has to remove two electrons to become stable. To remove the first electron, the ionization potential is less. You don't need so much energy. But to remove the second electron, you need more ionization potential. It's harder to remove the second electron than the first electron. The unit of ionization potential is electron volt. Okay, that's how they measure ionization potential. It's the amount of energy, no? Unit of energy. One of the unit of energy is electron volt. You have studied any other unit of energy before? Have you heard of joules? Joule, calorie?
Yes, last year it was.
Yeah. So these are all different units for energy. And for measuring amount of energy present in electrons or energy required to remove an electron, all these are very small amount of energies, right? So for that, we use this small unit, which is called electron volt. One electron volt is like 1.6 into 10 raised to minus 19, if I'm not mistaken, that many joules. So into 10 raised to minus 19 is a very small number, right? That is the unit uh, electron volt. Okay, so this is what we saw. As you go, it said, as you go down the group, what happens? Atomic size increases, right? Because the number of orbits increase. And due to that, ionization potential decreases because the nuclear attraction of the outermost electrons is less as you uh, increase the orbits. Hence, the outer electrons are loosely held, and so less ionization potential energy is required to remove that electron. As you go down the group, nuclear charge increases because there are more protons and more electrons, but that does not make too much of a difference to the outermost orbit because orbits are increasing. And even though the nuclear charge is increasing, ionization potential energy is supposed to increase, but the outermost orbit is too far away from the center, and there's less energy holding those electrons. Yeah. All right. Any doubt in this? See if I'm drawing these two. Okay. Sodium and potassium. Which one has more nuclear energy? Just nuclear energy. I'm not talking about the attraction to the outermost electron. Which of these two have more nuclear energy? Sodium or potassium? Potassium. Why? Sodium has how many protons? Sodium has 11. That's the atomic number. Potassium has 19. That is its atomic number. So 19 is clearly more than 11. So potassium has a higher nuclear charge. But if you look at the attraction between the atom and the outermost orbit, and here also sodium and the outermost orbit, which has more attraction? Sodium. Even though potassium has a higher nuclear charge, sodium more strongly attracts that outermost electron towards itself. Why is that? Less orbits. So that outermost electron is closer to the center. So there is more attraction towards the center. Okay. So as you go down the group, even though nuclear charge increases, that does not make so much effect in that attraction to the outermost electron because of the orbits. Okay, that is more what we say. There's a word used here. Yeah, that dominates. The increase in the number of orbit that dominates the nuclear charge. Okay. Okay, let's look at how it's in your book. Yeah. So in page number 12, you can see again they're explaining two factors which ionization depends upon. What are the two factors which it depends upon? Atomic size and nuclear charge. As I said, in every trend, you will see these two things, atomic size and nuclear charge. Now look at the table over there. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Okay, they have given the second period elements, and under that they've given the ionization energy. So here in my book it is 5.4, in your book it is 520. So they've used a different unit.
Sir, which one are you doing?
Page number 12. Trends in ionization energy across a period. Instead of using electron volt, they've used, what is the unit? Kilojoules per mole. Is that some other unit? Okay. That unit is just into 100 of what this is. See, this is 5.4 into 100 is 540. So around 540, it's 520. Is that? Next one is 9.3 here. So it's supposed to be 930. How much is it? 899.
What is the page number?
What is what?
Page number?
Page number 12. Anyway, wherever it is, look as you go to the right, what is happening to the ionization potential? It's increasing. There are some exceptions. Like if you see beryllium is 9.3, it's more than boron. Okay. So in all these trends, there are some exceptions which have no reason. Okay. But generally, you see the trend that the ionization potential energy is increasing as you go to the right. In your book, you have the third period also. Sodium, magnesium, aluminum, silicon. And there also you see a general trend of increasing as you go to the right, other than the exceptions. Two of them have exceptions, that is magnesium and phosphorus. You see there's a star next to the number. What does star represent? Exceptions. Now it's written there, right? Okay. So over here, you can see that as you go completely to the right, that is neon has the highest ionization potential energy. Why is that? Why does neon have the highest ionization potential? Yes, stable. So it's not. Yeah, there's so much nuclear charge that holds these electrons together. And does neon ever want to give that electrons away? No, it's already stable. It needs all those 8 electrons to keep it stable, right? And so these electrons are very tightly held to the nucleus because of the high nuclear charge. Okay, so neon has the highest ionization potential. Okay, we'll go to the next factor. Sorry, next trend. Your book is, let's see, electron affinity. Okay, number 5. Because they're all related to each other. Okay. Remember what was ionization potential? It was the amount of energy required. Required for what? To remove an electron. Electron affinity is exactly the opposite. It is the amount of energy released when an electron is added to an atom. Okay. This is the first atom, second atom, A, B. If A is removing an electron and transferring it to B, to remove the electron from A, what do you need? You need energy to remove that electron. It requires energy. But at the same time, if an electron is added to B, their energy is not required, it is released. It gives out energy. So opposite of required is released. Okay, so that's what we are seeing over here at B. It is the amount of energy released when an electron is accepted or added to the B. Okay, now A will turn into a cation and B will
So
turn
when
into
B is
anion.
accepting the electron, so it is releasing also.
Pardon
When
me?
the B is accepting, when the B is accepting the electrons, so it is releasing also.
Energy is being released. Energy. Okay.
Okay.
So to remove an electron from A, you require energy. When an electron is added to B, it releases energy. Okay. So in A, the amount of energy required is called ionization potential. At B, the amount of energy released is called electron affinity. Any doubt in that? Let's read the definition. What is electron affinity? It is the amount of energy released when an atom in the gaseous state accepts an electron to form an anion. Right. Here, A becomes a cation. Cation means positively charged because it lost the electron. And here B becomes an anion because it got that electron and turns negative. Okay. So the reasons are same, just like how we.
Can we read from our book because I'm not getting that definition.
You understand the concept first, then we will look in your book where what is. Okay. Just understand what it is. Understand the definition, understand the meaning, and then we'll just compare it with your book. Now you can give the same reasons as you're going down and to the right. Exactly the same thing is happening. As you go down the group, what happens to ionization? Sorry, electron affinity? It increase down. Same like this. Same properties here. As you go down the group, decreases. Just memorize this. We will see why. As you go down the group, decreases. As you go to the right, increase. Okay. So let's see why. So page number 12 in your book, electron affinity or electron gain enthalpy. So again, same two properties. Electron affinity depends upon atomic size and nuclear charge. You can just give the same reason for everything. So atomic size, the smaller the atomic size, the greater the electron affinity, because the effective attractive forces between the nucleus and the valence electron is greater in smaller atoms. And so the electrons are held firmly. So this like how ionization potential made more sense about removing an electron, you need more energy and there's more nuclear charge holding it. Same reasons are given here, but you can't understand it very clearly as you understood ionization potential. Okay, but you can give the same reason. As you go to the right, nuclear charge increases. So there is a more force of attraction towards the center. And because of that same thing, when an electron is added, it releases more energy. So it doesn't make so much sense, but you can just give the same explanation as ionization potential. Okay, as you go to the right, what happens? Nuclear charge increases. If nuclear charge increases, everything increases. The amount of energy required to remove increases. The amount of energy released when an electron is added also increases. As you go down the group, what reason you will give? You will talk about atomic size.
Size decreases.
Atomic size
Increases.
increases. Okay, so the effective nuclear charge between the center and the outermost electron, that decreases, lesser force of attraction, and because of that, electron affinity also decreases. Okay, so just it's easy to memorize the trends. It's same for all what we're going to see next. It's going to be the same. As you go down, decreasing. As you go to the right, increasing. Okay, for ionization potential, for electron affinity, and even for the next one. Okay, so what is is there any table here? Yeah, look at the table in electron affinity, page number 13. So here also electron affinity is the amount of energy. So they're using the same unit in your book, that is kilojoules per mole. In my book, again, it is electron volt. What happens as you go to the right?
Decreasing.
As you go to the right. So don't look at it as a negative number. If you look at negative numbers, it's decreasing. But look at it as a negative charge. So bigger the number, more the charge. And they put a minus because it's a negative charge. Okay. Bigger the negative charge, bigger the value, bigger the energy. Okay. So here minus 0.6, small charge. As we go to the right, there are some exceptions, but generally it's increasing, minus 1.25, then minus 1.48, and minus 3.6. So that number is increasing. Okay, so electron affinity is increasing as you go to the right. In your book, it's just into 100. So lithium is minus. You see it, page number 13. What is the electron affinity for lithium? Minus 60. And look at the trend as you go to the right. Minus 88, minus 122, minus 141, and minus 328. So there is an increase in electron affinity as you go to the right. It's written in negative because it's a negative charge. Now, as you go down the group, look at the first group, hydrogen, lithium, and sodium. What's happening to that number? Huh? It's decreasing, minus 73. See, 73 is a bigger value. Then minus 60 and minus 53. So as you go down the group, there is a decrease in the electron affinity. Look at the last group, sorry, seventh group, halogens. Fluorine is minus 328, and as you go down, it's supposed to decrease, no? Chlorine. Yeah, that's an exception again, only chlorine. Here you can see more, minus 3.6, minus 3.8, it increased, but then after that, it's decreasing. Okay, so generally the trend is as you go down the group, electron affinity decreases, but again there are some exceptions. Same reasons you will give as as the ionizing potential. As you go atomic radius, yeah, as you go down the group, atomic radius, as you go down the group, atomic radius, what happens? Increases, and so because of that, electron affinity decreases. As we go, yeah, same down the group, nuclear charge increases. If nuclear charge increases, electron affinity should increase, but the increase in atomic radius dominates over that. And so you see that there's a decrease in electron affinity as we go down the group. Like overall nuclear charge is decreasing as you go down the group. Exactly same reason, right? As ionization potential. Look at neon. Why is neon 0? No ionization, no electron affinity. It does not take electrons, right? So 0. Only when it takes electrons, the energy is released. Neon is already complete. All the noble gases have 8 electrons in the outermost orbit. They are complete. They don't release energy because they don't take any electrons. Okay. So be careful about the noble gases. They're different every time. For ionization potential, it was proper. This is the amount of energy required, and yes, you need a lot of energy to remove an electron. So you see that there is a high ionization potential. But for electron affinity, 0. Supposed to be high according to the trend, but why is it 0? Is because they don't take electrons, so they don't release energy. Let's just write down in short what is ionization potential and what is electron affinity. I'm just writing one word to help you remember the definition. Ionization potential is energy required. That should help you to remember the whole definition. Okay, what is ionization potential? The full definition? It is the amount of energy required to remove an electron from the outermost orbit of an isolated gaseous atom. Okay, that's the full definition. Isolated means gas that's an atom that's alone, and gas. Okay. For electron affinity, what is the short definition? What you should write? Energy released.
When atom in gaseous state gains electron to form an anion.
Yeah. Yeah. The whole definition: amount of energy released when an atom, when isolated gaseous atom, what attracts? Huh? Is it attracts?
And gaseous
Yeah. Accepts an electron. So amount of energy released when an isolated gaseous atom accepts an electron to form an anion. Okay. Did you write down this one? Just note down this trend. Okay, we'll go to the next trend, that is electronegativity. Okay, now this is not amount of energy or anything. Okay, this is a tendency of an atom to attract electrons. That's all. What is electronegativity? Tendency of an atom to attract electrons. See, now when an atom attracts electrons, what charge does it get? What charge does the whole atom become? Negative. You see, that's where the word electronegativity. Okay, it wants to be negative. Why does it want to be negative? To stay stable. See, because if it has like chlorine has 7 electrons. It wants to attract that 1 electron and become 8. Its aim is to become stable. Yes, it will become negative, but that's not the priority. It wants to become stable. Okay, so that tendency to attract electrons is called electronegativity. Okay, so let's read the definition. The tendency of an atom to attract electrons to itself when combined in a compound. Right, when A and B join, A and B become a compound, AB, right? In that compound, B has the tendency to attract electrons. Let's look at your book, page number 13. Same definition. The tendency of an atom in a molecule. The molecule means that compound, right? So tendency of an atom in a molecule to attract the shared pair of electrons towards itself is called as electronegativity. Okay, so here they're talking about a covalent compound. Here the definition looks like an electrovalent compound. Electrovalent means what? One atom is donating electron, the other atom is taking an electron. Okay, so the definition looks more like they're explaining about an electrovalent compound. In your book, the definition looks more like they're explaining about a covalent compound. Covalent compound is when there's sharing of electrons. When sharing of electrons takes place, how it is? There are two atoms, both will share one electron each. Okay, but one of them, the one which is more negative, will pull those two electrons towards itself. That's how the definition is here. Let's read that again. The tendency of an atom in a molecule to attract what electrons? The shared pair of electrons. Who's sharing? Both the atoms are sharing, and those electrons are supposed to be in the middle. But what's happening? One of them attracts those shared pair of electrons towards itself. Okay, so that is electronegativity. For me, this definition makes more sense, which is here. Tendency of an atom to attract electrons towards itself when combined in a compound. Okay, so write that definition here in your book. The trends are exactly same as before. As you go down the group, electronegativity decreases because atomic size increases. Same reason, same trend. As you go to the right, electronegativity increases because nuclear charge increases. They can attract, I mean, they have more tendency to attract electrons towards itself. Look at the table in your book, page number 13. There is a big table on the right side. You can see all the electronegativity values for so many elements. Okay, it's almost like the whole periodic table they have put over there. 1, 2, 13, 14, 15, 16, 17. That is the first 7 groups. First group, second group, third, fourth, fifth, sixth, seventh group. Okay, third group is called 13th group. Fourth is 14th group, right? So there, let's look to the right. As you go to the right, look at the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen. What's happening to the electronegativity as we go to the right? It's increasing, no? Look at this next period: sodium, magnesium, aluminum, silicon. 0.9, 1.2, 1.5, 1.8, 2.1, 2.5, 3.0. You see that increase? Okay, and last, argon.
Yes, sir.
It's not there in your book, but argon would have how much electronegativity? The noble gas. What will be the electronegativity? 0, because they don't have any electronegativity. They don't want to attract electrons towards itself. It's already stable. Okay. Yes, and if you go down the group, look at 7th group, 17th group: fluorine, chlorine, bromine, iodine, astatin. What's happening to the electronegativity? It's decreasing. Okay, reasons exactly same, so we don't need to go through it. Exactly the same in your book. In fact, it's not even there. It's written over there, same as before. Where is that? Or in this book? Yeah, here, see, reasons affecting electronegativity are the same and in the same order as the electron affinity. So they have not written it again. It's the same explanation. So just write it, just draw the arrow down and say decrease, and to the right you write increase. We're not writing the reason because it's the same. So if you look at the whole periodic table, which of these elements are electronegative? All the ones on the right, they're electronegative. All the electronegative elements are non-metals. Where are the non-metals? This right side part, correct? And all the elements on the left side, they are opposite of electronegative. That is what? They're electropositive. That's also a word. Okay, all metals are electropositive. All non-metals are electronegative. Okay, why are non-metals electronegative? Because they have the tendency to attract electrons. Why are the metals electropositive? Because they have the tendency to release or donate or give away electrons. Okay, so what is the trend in electronegativity as you go from left to right? What happens to electronegativity? Increases. What happens to electropositivity as you go from left to right? Decreases. Right, electropositivity is opposite. But you don't have a trend called electropositivity, but that's how it would be, right? Down the group, what would happen? Electronegativity decreases because atomic size increases. What about electropositivity? As you go down, that also will decrease because the size increases, the atomic size increases. Okay, so for electropositivity, it is decreased both ways. To the right also it's decreasing, downward also it's decreasing. Okay, just remember that it's not mentioned, but keep that in mind. Okay, the next trend is metallic and non-metallic character. Those are the last two trends. So for that, you have to go back to the second and third trend in your book. That depends on what we just spoke. Easy to remember. What happens in the periodic table? As where is metals, where is non-metal? Let's look at the metallic character first. What happens when you go from left to right? What's happening to the metallic character? Increases. Are turning into non-metals. So metallic character is decreasing when you go from left to right. Just very easy to remember. If anything decreases to the right, then downwards it will increase. If it increases to the right, then it will decrease as you go down, except for electropositivity, which is not even there. Okay, but for all the trends that you have, that is how it is. Okay, so it's easy to remember, easy to memorize. So let's talk about metallic character again. As you go to the right, what happens to metallic character? Decreases. So when you go down, it increases. Okay, now let's see why. Yeah, you can clearly see this trend for the fourth group. If you see the fourth group, okay, see on the fourth group, carbon, silicon, germanium, tin, and so on. So this carbon is a non-metal. Silicon, metalloid. Germanium, metalloid. Tin, metal. You see the non-metal is changing into a metal as you go down the group. In other words, metallic character is increasing. Non-metals are turning to metals means what? Metallic character is increasing. And non-metallic character is decreasing as you go down. Okay, so metallic character is increasing as you go down, and non-metallic character is decreasing as you go down. Non-metallic character is decreasing because you can see the non-metals are changing into metals.
And
Okay.
metallic character is increasing.
Increasing as you go down. Open your books to page number 8. In that, look at metallic character. Just read through that metallic character and the non-metallic character. I will just come in a few minutes. Pass this book. Go through all the trends. Okay, first you read metallic and non-metallic character and then learn the rest. Why does the metallic character, okay, what happens to the metallic character as you go down the group?
Increases.
Metallic character as you go down the group?
Increases.
Increases. Okay, why does it increase?
You project stronger material.
Yeah, but why? As you go down, metallic character increases. Why? What's the meaning of metallic character? Or when do we say a metal has a strong metallic character?
To lose their valence electrons.
Yes, the easier it lose their valence electrons, the more metallic character it is. Okay, so as you go down the group, the nuclear charge decreases. So those the electrons in the outermost orbit, they lose, they're easily lost. As you go down the group, the electrons in the outermost orbit are easily lost with less ionization potential energy, right? And so they easily become a metal. That's why when you go down the group, metallic character increases. Okay. And when you go to the right, why does the metallic character decrease? Because they don't like to lose electrons. As we go to the right, they want to gain electrons. Right. So it's all about how easily or how hard they are able to lose their electrons. Okay. What about non-metallic character? As you go to the right, what happens? Increase. They want to attract electrons. They want to gain electrons. So they become negatively charged. So the non-metallic character increases to the right. And when you go down, why does it decrease?
Has to lose electrons.
Yeah, talk about electrons losing or gaining. As you go down, how is it? Look at the seventh group, that is halogen.
Gain, but it is losing.
Wait, let me just go to that part. In non-metallic character, down a group. I'll just read that. It's in page number 9 on the left side down. The atomic, okay, down a group, the atomic size increases due to the addition of new shells over successive periods. Yes, we know that. Though the nuclear charge increases due to an increase in atomic number, the effect of an increasing atomic size is greater. Therefore, non-metallic character decreases down the group. Okay, so there's not too much explanation. But as we go down the group, orbits increase, nuclear charge decreases, and you need less energy for anything to happen. It is to remove an electron also you need less energy. When an electron is added also, less energy is released. Less energy means non-metallic character decreases down the group. Some of them don't make sense. Like there's no proper explanation also. But you can just remember all the trends very clearly. Okay. So for metals, it's clear. As you go down, as you go to the right, it's clear. Non-metals, it's clear when you go to the right. When you go down, increasing atomic size, therefore non-metallic character decreases. That's all is written. Okay.
Non-metallic character.
Yeah, when you go down, non-metallic character decreases. How will you remember this? You just have to remember that to the right and to the down are opposites of each other. Okay. And yeah, so go to the last page. There, all the trends are written together and see which all trends are similar. Page number 14. Page number 14, you have the table. Okay, so you see atomic size and metallic character have the same trend. Atomic size and metallic character. When you go to the right, both of them decrease. All the others, when you go to the right, increases. All the others means ionization potential, non-metallic character, electron affinity, and electronegativity. They four are the same. Same way when you go down, look at the next table at the bottom. They're also same. Atomic size and metallic character, when you go down, what happens? Increases. All the others, when you go down, decreases. Okay. That is what is important because you're going to use that to arrange elements in order. They won't ask you why this and why that. Two things they can ask. One, they can ask you the definitions directly. Second, they can ask you to arrange elements in order. And then whatever they ask could be based on the periodic table. Fill in the gaps. What is the valency of this element? What is the number of electrons in this element? So it's all basic stuff that they can ask from this chapter. Okay. All right. Now what I'll do is I'll give you some elements and we're going to arrange them in a particular order based on these trends. Have you memorized all the trends? Which two are same? Atomic size and metallic character. And what the other four are same? What are the other four? Non-metallic character, ionization potential, electron affinity, electronegativity. They are the same. Okay, that we can easily remember. Page number 20, question number 8. In my book, it's this one. 2009, question 2. So what have they given here is they've given the structure of a periodic table.
Sir?
Yes.
In our book, which question?
Question 8. Page number 20, question 8. Okay. All right. So here some of the elements have been mentioned. You can see lithium, magnesium. Some of the elements are there, and for the rest of them, they've just put A, B, C, D, E, F, G, H, I, J, K, L. Okay. All right. First question. Here, some elements are given below. Okay. First question: which is the most electronegative out of all these elements? Which is the most electronegative?
J.
JK.
Yeah, electronegativity increases as you go to the right and decreases as you go down. So, which is the most electronegative element here? Neon is supposed to be. If you go through the trend, then neon is supposed to be, because as you go to the right, it increases and down it decreases. So the top right corner will be the most electronegative. But neon is a noble gas. It's not electronegative at all. It doesn't want to take electrons. So what's the one next to it? J. Don't need to write the actual element. Just write J. J is the most electronegative. Understood?
Yeah.
Okay, next. How many valence electrons are present in G? Easy one. G is on 15th group or 5th. So how many valence electrons? 5. Valence electrons means electrons in the outermost orbit. Correct. So 5th group means 5 electrons in the outermost orbit. 6th group means 6 electrons. 7 means 7 electrons. And last 18th group means 8 electrons in the outermost orbit. Okay, so that's an easy one. In your book, different questions are there. We'll see the questions from here first. Okay. Next, write the formula of the compound between B and H. B and H. B is in the first group, H is in the 6th group. So what will be the formula of the element or the compound between B and H? B and H. How do we write the formula? Crisscross method. So we need to know valencies. What's the valency of element B?
1 plus.
1 plus, because it's in the first group. All elements in first group are 1 plus. Second group is 2 plus. Third group is 3 plus. Fourth group is 4 minus. Fifth group is -3. Sixth group is -2. Seventh group is -1. Okay, so H, what's the valency of H? -2, right? And now crisscross method, B will get the 2, H will get the 1. So B2H is the formula. Got it? Next, in the compound between F and J, what type of bond will be formed? Bond, 2 types of bonds. You have covalent and electrovalent. So B and J. B is here. Oh, F and J. Okay, F and J. What is F? Metal or non-metal? What's under that? What's under silicon?
Like chlorine.
Under silicon is germanium. So this is germanium is a metalloid. And J is a non-metal. Okay, so what is the bond between a metalloid and a non-metal? See, if it is a metal and a non-metal, what's the bond between a metal and a non-metal? Huh? Electrovalent. And between two non-metals, it's covalent. Come on, that's the basic thing. Knowing that only you can answer this. But here it is between a metalloid and a non-metal. Okay, so let me just check that. Write down that if you don't know. Electrovalent or ionic is between metal and non-metal. Write that down. Electrovalent or ionic, which is the same thing, is a bond between a metal and a non-metal. And what about covalent bond? Between two non-metals. But covalent could also be between a metalloid and a non-metal. Okay,
But what is the bond between metal and metals?
there is no bond. They don't join. Metals and metals also don't join. So between metal and non-metal, what is the bond?
What is the valent and non-valent?
Electrovalent. Between non-metal and non-metal,
Um,
covalent. Between metalloid and non-metal,
oh,
covalent. Okay, so this answer is what? Between F and G. It's covalent because it's a metalloid and a non-metal. Okay, we'll answer the questions from your book now. Second question. Identify the most reactive element of group 1A or 1. Which is the most reactive element? 1A.
lithium.
What do you answer? B. As you go down the group, the reactivity increases because it can see that electron in the outermost orbit is loosely held. It can lose that electron easily. And so it loses it, and that means it's more reactive. Not only that, I showed you the video of putting these metals in water. What happens, right? The reactivity increases as you go down. You don't know, I mean,
Yeah, I forgot.
no, but the video you've seen or what? When you put a metal in water, it just blasts and it gives out a. So as you go down the group, the reactivity increases. Okay. Next question. Listen carefully. Identify the element from period 3 with the smallest atomic size. Easy one. Period 3. Which is period 3 here? A, Mg. That is period 3. So which has the smallest atomic size? K. As you go to the right, the size decreases, no? Next, identify the element with the highest ionization potential.
Lithium.
No. Highest ionization potential. See, huh?
Helium.
K is in the middle. Why would it have? What is it?
More
What is ionization potential? You should first think of the definition. What is it?
energy by
Yeah, energy required to remove an electron. So which one will need the most energy required? Which will require the most energy to remove an electron? Hmm? L, J. No one else has the answer? The answer is neon. Neon will require the most energy to remove an like you cannot remove an electron. It will not give it away now because it's already stable. So neon is the answer here. For electronegativity and electron affinity, you should just forget the 18th group. The answer will be J. Okay, but for ionization potential, you have to include that noble gases. Because ionization potential is the amount of energy required to remove an electron. And yes, you need the most energy to remove an electron from neon. But if it is energy released or tendency and all that, the other two definitions, noble gases don't come over there because they don't accept electrons. They don't want to accept electrons. Is that clear, everyone? Okay. So for ionization potential energy, you include the noble gases. For the other two, that is electron affinity and electronegativity, you only include till 7th group. Don't include that 18th group. Clear, everyone? Next. How many valence electrons are present in Q? Easy one. Q, where is Q? There's no Q. Q? There's no Q only in the question. Okay, let's change that from Q to G. How many valence electrons are present in, sorry, how many valence electrons are present in, okay, G? 5. Right, group number.
Yes.
Next, which element from group 2 will have the least ionization energy from group 2? As you go down the group, ionization potential energy or ionization potential decreases. Okay, so C has lesser. Identify the noble gas of the 4th period. Yeah, but they're saying identify the noble gas. So what is L? What is the actual name? Answer is krypton. Okay, krypton. Okay, next. In the compound between A and H, what type of bond is formed? A and H. We did B and H. A and H. Come on, keep telling.
Covalent.
Okay, what type of bond? Yes. What type of bond? Electrovalent, because it's a metal and a non-metal. Next, give its molecular formula.
So you are teaching more?
No, we'll be stopping now. Tell me the formula between A and H. Others? See, you should do it the same way I did it over here. Write A and H, put their valencies, do crisscross method, you'll get the answer. So A and H is same like B and H, because A and B are both in the same group. So A2H. Draw the electron dot structure for the compound formed between C and K. Electron dot structure you will learn in the next chapter. Okay, so omit that question for now. When you do the next chapter, you'll understand that. The other type of question which can come here is they'll give you elements and you have to arrange them in order. Okay, suppose I'm giving this P, S, Al, and Cl. First thing is you have to figure out where they belong. Which group, which period? Where do they belong?
Period 2.
No. Period 3. They're in period 3. Look at the period 3 here. Do you see phosphorus, sulfur, aluminium, chlorine? See, first thing is identifying where they are found. Okay. Now, if the question is arrange them according to decreasing order of electronegativity. Arrange according to decreasing order of electronegativity. So how will you arrange them in decreasing order of electronegativity? Left to right or right to left? Yeah, right to left. Because if you go from left to right, electronegativity increases. Other way, it decreases. Yeah. So write the element on the right first, which is that. Which element is on the rightmost? Chlorine. Then
Aluminium.
no, aluminium is on the leftmost. See here. Chlorine is on the right, then sulfur, then phosphorus, and then aluminium. Okay, and now since it's decreasing order, this is the symbol you have to put. Because it's getting lesser. Clear with this, everyone? Just wait, okay? Is it clear how to do this? Suppose the question was increasing order, then you have to put this symbol, increasing, like this. Getting bigger. Decreasing, you have to put this sign. Okay, so write this one question, and then you can end. Yeah.
Thanks.
Okay, so remember this thing, metals get oxidized, non-metals get reduced. How I remember this, no? I think of metals, when metals are outside in the water and in the rain, what happens to the metals? They get rusted. What is the meaning of rusting?
They get oxidized.
Getting oxidized, right? Rusting is addition of oxygen. So that is also one way to remember. Metals get oxidized and non-metals get reduced. Okay, I'll just repeat that because I had not recorded. So metals get oxidized. What do you mean by oxidized or oxidation? There are three meanings for it. Oxidation could mean addition of oxygen or removal of hydrogen or removal of electrons. So two ways we have seen examples of how metals get oxidized. One is metals, they donate electrons. Donating electrons means removal of electrons, which is oxidation. That's one way to remember. Second way to remember is metals get rusted. Rusted also means addition of oxygen. Okay, so you can remember any of these two, either removal of electrons for metals or addition of oxygen, both which means both are oxidation. Okay, so coming back to our question here, give reasons. The oxidizing power of elements increase from left to right across a period. Okay, yeah, so now listen here. We just now spoke about oxidation or getting oxidized. Okay, here they're talking about oxidizing power. Oxidizing power means something that is able to oxidize other things. For example, let's talk about me and Aman. Okay, now if I am able to oxidize Aman, what happens to Aman? He gets oxidized. If I have the oxidizing power, what happens? I'm able to oxidize something. So if I'm oxidizing Aman, what happens to Aman? You get rusted. Okay, you get oxidized. You understand? So you are the metal. Metals get oxidized or rusted. What am I? I'm a non-metal. So non-metals have the oxidizing property and they're able to oxidize metals. Correct? So the question here, the oxidizing power of elements increase from left to right. See, when you go from left to right side, you're getting non-metals on the right. So non-metals have more oxidizing property. Okay. So why
We call it
what is
agent
that?
or something.
What
Can we
Nathan?
call it oxidation agent or something?
Yes, correct. Oxidizing agent. I am called an oxidizing agent because I'm able to oxidize something else. Okay. So non-metals are oxidizing agents. They can oxidize metals. Okay. The question is why are they oxidizing agents? Why are non-metals oxidizing agents? Your answer is written here. Let's see this. Because the tendency of an element to take electrons from metals. Okay. So non-metals have the property of taking electrons from the metals. Right. Non-metals want electrons. So when non-metals take electrons from the metals, what's happening to the metals? They're getting oxidized. So that's why non-metals are good oxidizing agents because they can take electrons from the metals. Is that clear, everyone? Non-metals don't get oxidized because to get oxidized means to give out electrons. Do non-metals give out electrons? No. Now, non-metals can get combined with oxygen. So we can call it oxidation, I think, because see, like for example, nitrogen, sulfur, they all can get attached with oxygen, right? So they can get oxidized, but its oxidizing property is not very strong. Because see, non-metals don't join with non-metals very easily. Sulfur, nitrogen, all of these are non-metals. And if non-metals have to get oxidized, it's like a non-metal joining with a non-metal. Can that happen? Yes, it can happen. But that bond formed between them is not very strong. What is a bond formed between a non-metal and a non-metal called? Covalent bond. These covalent bonds are not very strong. So non-metals can get oxidized, but that oxidized new element compound is not a very strong compound. Okay. Whereas metals, they get oxidized and it forms a very strong bond between that oxygen. For example, sodium. Sodium joins with oxygen to form sodium oxide. Now, what is the bond between the sodium and the oxygen? It's an electrovalent bond or an ionic bond, which is a very strong bond. Okay. All right, next. Select the correct answer. Across a period, the ionization potential increases, decreases, or remains the same. Across a period means from left to right. What
Do
happens to
metalloids
ionization?
get oxidized?
What?
Do metalloids get oxidized?
Metalloids also could get oxidized. Silicon can join with oxygen to form silicon dioxide. Yeah, everything can get oxidized. But how it is, the metals can get oxidized more. Non-metals, less. Yeah. Metalloids obviously in between. All right. So what is the answer for this? What happens when you go across the period? Ionization potential? Hmm?
Increases.
Increases, right? As you go to the right, we wrote all the trends yesterday. As we go to the right, all of these things they increase. Ionization potential, electron affinity, electronegativity, and non-metallic character. They all increase to the right. Correct? Okay, next. Down the group, electron affinity decreases. Same for ionization potential, electron affinity, non-metallic character, and electronegativity. Okay, next. Choose the correct answer from the choices given. In the periodic table, alkali metals are placed in which group?
One.
One, right? First group
One.
elements, they're called alkali metals. Group 2 elements, what are they called? Alkaline earth.
Alkaline earth.
Alkaline
Then
earth.
group 7A or 17, what are they called? Halogens.
Halogen.
Then group 18 or 8A or 0 group, inert gas,
Noble gas.
noble gas, rare gases, that also. Okay. Next, which of the following properties do not match with elements of the halogen family? Which of the following properties do not match with the element of halogen family? So what we know about halogens? 7A, 17th group, 7 electrons in the outermost orbit. Valency is what? For halogens, what is that valency? -1. Okay, so keeping this in mind, read all these A, B, C, D and tell which is false.
Anna, some people say that hydrogen is also a halogen.
Yes, hydrogen is a confusion. We don't know where to put it, whether we should put it in the first group or 17th group, because it shows some properties of 1A and some properties of 7A. That is one of the problem with the modern periodic table. So what's the answer for this?
C.
C is metallic. Are halogens metals? Halogens are to the right, so they are non-metals. Okay, so that is false. Everything else is correct. See, they have 7 electrons. Yes. B is they're highly reactive chemically. Yes, everything in one group and 7th group, they're all highly reactive because they just need one electron to either donate or take. That's easy. So they are very reactive. Then D is they are diatomic in their molecular form. Diatomic means 2 atoms join to form the molecule. For example, chlorine. What's the formula for chlorine? Cl2. 2. All nonmetals. In fact, all nonmetals are diatomic. Exceptions are there, like ozone is O3, phosphorus is P4, and sulfur is S8. But other than these three, all nonmetals are diatomic. Hydrogen is what? H2. Oxygen, nitrogen, iodine, I2. Bromine, Br2. What other nonmetals are there? Sulfur is an exception. Yeah. So all nonmetals are diatomic. So here they're saying halogens are diatomic. Yeah, it's true. Okay. Next, state the group and period of the element having 3 shells with 3 electrons in their valence shell. What's a group and what's a period? Three shells means
Third period.
38. 3 shells means which group or which period?
No, Anna, I said third period.
Third period, okay. Yes, 3 shells means third period. All the elements in the third period have 3 shells. And 3 electrons in the valence shell means third group. Right. Every element in the third group, that is 3A, has 3 electrons in their valence shell. Okay. All right. So 3A, no, 3A here, not 3B. You're saying 3B. Third group means we're talking about 3A group. Yeah. All right. Any doubt? I think we have done most of the questions from this chapter. Okay, you should be clear with this. You understood how the questions can be. It's all quite easy, right? You have noticed? This is the easiest chapter in chemistry. It's a scoring chapter. So you should get full marks in this chapter in your exam. Okay, go through the chapter clearly and be sure with this chapter. Okay.